Hello everyone, my name is Amit Tyagi. My project topic is case study in fraud prevention. So to start with the problem here, right, what exactly I'm trying to solve. Uh, so at a overarching problem here is to identify and classify the rare events. Rare in terms of like you have a large data set and the events that you are looking for, you're trying to classify are rare, right? So your data set is very imbalanced, right? So for these two classes, uh, this data set is very imbalanced, normal versus fraud, normal versus anomalic, right? So most of the machine learning models for classification prediction that we have today, like random forest classifier, for an example, right, cannot classify these rare events. Reason, there's not enough label data available to learn and recognize the patterns of these rare events. Right? Now, this was a particular use case for me because in my company, Verizon, there are a lot of areas where we need this particular area, this particular technology, this particular implementation. Right. So we have different analytics organizations, but when it comes to fraud detection and anomaly detection, we are not doing good. I wanted to focus through this program, look at how we can build a solution around anomaly detection. That was the reason I chose this topic. So the practical use case, for example, in my company itself are device fraud, credit card fraud, identity fraud, security fraud, right? Other area is we have applications, right? And you have hundreds of servers and you have thousands of APIs, and each API is giving errors back. But depending on the load, so you want to know when your ecosystem is unstable, when you need to enable your failover strategy, right? So you should be able to tell when some of your the total number of errors at this point are too much or anomaly. So this is anomaly now in system. So you need to look at if something's wrong with the APIs, something's wrong with the servers, right? So the volume, the call volume in the servers is in billions a day, right? And number of errors at any given point, if you do 5-minute average, it's in hundreds of thousands. So just being error is not a problem. Finding that anomaly, that high, very high rate of errors, that varies by your total load during daytime, nighttime, evening, during sale season, and whatnot, is entirely different set. So finding anomaly, those rare pattern is the main use case here. For this particular implementation, I use the data set available on Kaggle. It's a credit card usage data from European countries. Approx 285K transactions. Out of those, 492 are fraud. So you can see events, these fraud events are about 0.172% of total transaction, which is highly imbalanced data. The solution approach is autoencoders are very popular for this kind of implementation. There are not too many out-of-box solutions available, right? We have tried, Elk has XPack, there's a model HTM, but those are closed box solutions, did not work. So autoencoders are a good solution where the whole hypothesis is this, that you do encoding and reconstruct your input, right? And then calculate the reconstruction error. So the trick is you train your autoencoder on normal events, larger data set, like which is exponentially larger data set, and calculate the reconstruction error. When you run this model on rare events, fraud events, so the reconstruction error will be way high because this model has not been trained on these anomaly events, right? So your reconstruction, this model will not be able to reconstruct the input as good. So reconstruction error would be higher, and that then you try to find the threshold reconstruction error threshold, which can segregate, cleanly separate normal events versus fraud events or rare events. So here for error, we are using mean square error. There are many evaluation techniques to get to these thresholds. You have recall versus precision threshold technique. You have confusion metrics. Then there F1 score is one other. I'm using confusion metrics as the main basis to fine-tune this reconstruction error threshold. Configuration-wise, libraries, Python on my machine is 3.6.5. I'm using TensorFlow backend, Keras, sklearn library for the model evaluation methods, matplotlib to plot some graphs, and Seaborn for confusion metrics. Hardware perspective, as this model, I ran 100 epoch on this data set, and on my machine, it was taking about, on Windows, it was taking 5 seconds per epoch. So it was good. In fact, I ran this model on Google Colab 2. It was taking 6 seconds on GPU option. I was surprised. So my machine is i7 Intel processor, 8 GB RAM. And as I mentioned here, 100 epochs finished in about 400 seconds. Folder structure is pretty simple. I have main folder where I have my code, my data file. Then I have one folder for image. I'm using in my notebook, I'm using one image, recall versus precision and confusion metrics image. So that image is right here. Then there's a logs folder, and I'm using TensorFlow callback function for logs, checkpoints. So that's the folder it automatically creates. I'll go in detail for more detail into model now. So obviously, first basic libraries. If you look at the data set, the top data, basically it has about 31 columns and 285K rows. There are 2 columns. So these columns are already PCA applied. So for privacy reason, right? And 2 columns, time and amount, that credit card amount, usage amount is not anonymized. So, and we're gonna basically normalize the data. So we're gonna normalize those 2 columns in the range of 1, less than 1, greater than equals -1. Right? I'm using scalar function from sklearn, standard scalar, pretty common function. Then what I'm doing, I'm splitting my data set into train, validation, and test. So I'm gonna use train and validation for my training, and test when my model is ready. I'm gonna run test data set through it. So as I said before, the idea is to train autoencoder model on normal data. So from the training data, I'm removing the fraud events, and I'm dropping the class column. So you have only class column is your labels, right? So I just have the training data. For my final test data, what I'm doing is I'm adding those fraud events to my test data set. So I'm using Pandas concat function. I'm adding 2 data frames, test data frame and fraud data frame. I'm adding it together, which I will use when my model is trained, right? So this is my autoencoder model. This is similar to what we built in our classroom too, and it's not, it's shallow model, as we learned in classroom as well. I tried this particular model is 2 dense layers for encoding, 2 dense layers for decoding, and I'm using TON and ReLU as the activation function. I also tried, by the way, I tried various multiple variations of this model. I use more encoding and decoding layer. I use different activation functions. Plus, I use, in fact, rather than dense, I use RNN and LSTM layers. But this dense layer, this configuration seemed to be working better than any other model that I tried. This is my model summary. Input layer 1, dense, 2 dense layers for encoding, 2 dense layers for decoding. Total number of parameters is dealing is 835. Then I'm compiling my model, and I'm using callback functions for checkpoint. I'm saving the model as credit card fraud autoencoder.h5 file. I ran 100 epochs. I already talked about, you can see each epoch is taking about 5 seconds, 4 seconds. So overall about 400 seconds. This is training versus validation accuracy graph. It is about 70% accurate, but good thing is the overfitting problem is not there. This is pretty good. You can see the training and validation accuracy is kind of sort of overlapping. Same way if you look at the loss function, yes, it's a little bit different, but it's not that much of a difference between training and validation. Now, how to evaluate the model, right? So when you try to predict reconstruction, when you try to reconstruct validation data point, data set versus test data set. So validation, reconstruction error for validation data set, which are normal events, is, you can see this is in decimals, right? So mean is 0.70, right? 75% are 0.625, 0.627. That's a reconstruction error. While if you look at the test data, when I try to reconstruct the test data, predictive test data, which has the fraud events, you can see the reconstruction error is through the roof. It's to the tune of, if you see reconstruction error close to 1, is to the tune of plus 0.8. E8. It's not in minus. It's exponentially way too high. Anything which is close to, if you look at where true class is 0.09, which is close to 1, is going plus 0.7. So it's exponentially high reconstruction error. For I was happy and surprised how neatly, if you plot a graph or reconstruction error, normal versus fraud events, you will see these orange ones are the fraud events, they're exponentially high. You can see one E9, that's the scale here we are talking, right? So when I try to choose threshold here, when I try to play around with threshold, around 5,000, this is the result I got. With approx around 5,000, and I'm using the threshold, you can see the threshold fixed here. The value was 5,000, and code is in my notebook as well. All 492 events, fraud events, have been captured perfectly. There's no false positive, there's no false negative, or so they have true positive and true negative. Well, if I were using threshold about 100, 200, 300, I had false positives into 100 and 200 compared to the data set 57,200 or nothing. I mean, you can live with that sort of false positive as well. But perfect results I got around 5,000 threshold, right? So in summary, this model performed very good. True positive all, true negative all, false positive 0, false negative 0. But threshold is 5,000. I'm skeptic about it. This is very high threshold, but the reason is you will see the reconstruction error was through the roof, right? So that's the reason. Maybe for this particular data set, reconstruction error difference is so high. But this can be systematically automated. You can get these threshold values out, and you can see where you are getting confusion metrics. You can balance it. So we're very happy with the results. I hope I'm going to use this model for actual implementation. Similar model for the actual data as well in my company. Thanks for watching my video.